no smile, but then I thought that was like, it was accurate, but you smirk sometimes. You laugh. You don't act like you don't laugh. You look like you laugh.
I don't, wait, me laugh? I don't laugh.
No, your face looks like you and you're yelling at the physics students.
I'm yelling at the physics students. You'll have to be more specific. I haven't yelled at them this semester. But I'm. Huh. All right. Well, I will begin with a word of prayer. So. Heavenly Father, we thank you for this day again. I thank you for this class and just ask you to be with us. Help us to glorify you. We do this day, Lord. In your name I pray, Lord Jesus. Amen. All right. So last time we proved theorem. This was the argument principle 1, which said that the I'll skip the preliminaries and just get straight to the formula. 1 over 2 pi I integral of f prime of z over f of z dz is equal to n sub 0 minus n sub infinity, right? So what this did was it counted the number of poles, right? And it counted the number of zeros at once. It calculating this integral, I suppose I should specify the curve, you know, over some curve. And the deal is f has to be meromorphic on the curve. I mean, I guess I could state it like the boundary of a domain, right? It has to be meromorphic, you know, so you might have so suppose these are places where you have f of zj equals to 0, and then you've got maybe these other ones. I'll use some other letter. Let's see here. Z tilde. Right, and there we have z tilde sub j are, you know, poles, right? And in this case, you'd have, you know, so what in this particular instance, you'd have the multiplicity of z0 plus the multiplicity of z1 plus the multiplicity of z2 minus, you know, the order, I'll just call it order, of the pole z tilde 0 minus the order of z tilde 1 minus the order, I regret making so many, z tilde 2. Oh, that's it, okay. So this is the number of zeros counting multiplicity, you know. And this right here, I'll factor out the minus. It would be the number of poles, again, counting multiplicity. So, you know, if you had these 3 poles for your function, and one was a simple pole, and the other one was a double pole, and the other one was a double pole, you'd have n sub infinity is 5, you know. And if the zeros were each a triple 0, you'd have n sub 0 of 9. Okay, so this integral counts the number of zeros and the number of poles up to multiplicity. And we worked that out last time, right? Now, let's talk a little bit more about how this works. So if we look at the log of f of z, all right, so the log of f of z is going to be equal to the natural log of the absolute value of f of z plus I times arg of f of z. So please understand these calculations I'm about to make as being done with respect to a particular choice, a particular branch of the logarithm, all right? Whatever branch you pick, though, we can differentiate, right, that branch, and it all works out the same, right? Like the derivative of this is what? It's f prime of z over f of z, right? And on the other hand, we get is what? Like, you know, what's the derivative of that? Well, goodness gracious. d dz, I'll just write it this way, I suppose. d dz of the modulus of f of z over f of z. Oh man, I don't even want to write that. Just a second here. Yeah. I was like, this feels wrong. So it is wrong. So what I wanted to do is to take the differential of both sides, not the derivative. So the differential here, so I have the differential of the log of f of z, all right, is equal to the differential of the natural log of the modulus of f of z plus I times the differential of the argument. All right. Now, so if f of z is not equal to 0 for all z on a curve, right, then if we integrate this thing, right, so by the way, the differential, it's been a while since we talked about this, but the differential is just, you know, notation for df dz times dz, okay? But anyway, it's helpful to use the differential notation here just to get to the point more cleanly. So the integral of the differential around the curve, right, is equal to the integral along the curve of the differential of the natural log of this, all right, plus I times the integral along the curve of the differential of the argument of f of z. So the thing is, if the curve that we're talking about, and we are talking about a curve which is closed, right? And if f of z is not equal to 0, right? In this context, this integrates to 0, right? Because the natural log of the modulus of f of z is, in fact, an antiderivative for this integral, right? In other words, this is an exact form on the curve because we've assumed that f prime of z is not equal to 0. So the function natural log absolute value of f of z is continuous on the whole curve. But in contrast, so in other words, this piece goes to 0 because of that. But the other one, you know, that notation is a notation for a particular branch of the argument, right? And we know we can't have the same branch on the whole way around a loop, right? So there's no reason to, we don't automatically know that's 0. It might be 0, we just don't know, all right? And the larger point is that this is, let's see here. So this is almost, I mean, this, if you take the derivative, this is the integral of f prime of z over f of z dz, right? Because the chain rule gives me this. No matter what branch of the logarithm, it's always that, you know? So putting this all together and combining it with argument principle 1, that brings us to argument principle 2, namely that 1 over, let's see here, 1 over 2 pi I integral of f prime of z over f of z dz is equal to what? 1 over 2 pi integral of the differential of the argument of f of z, right? And then, of course, that's also n sub 0 minus n sub infinity. But that's not typically how argument principle 2 is written. Oh, there's neither? Hold on. There was an I there. And there's an I here too, right? I can't just drop that I, right? There's an I here. So careful. Don't poke your eye out. Great. So then what happens if we... Oh man, I'm sorry. Just a second. I'm not tracking something. All right, so 1 over 2 pi I, and there's an I here. So I'm dividing this equation by 2 pi I, right? The equation above, divide by 2 pi I get this. I get I over 2 pi I, and then, of course, this is equal to that because it's what we proved last time. Okay, so the i's cancel, and that gives us argument principle number 2. So theorem. It says that the integral over the curve of the differential of the argument of f of z is equal to 2 pi times the number of zeros minus the number of infinities. Again, counting multiplicity. Okay, so let me say again, you guys can turn in the mission that was due today if you want to tomorrow. I gave one of you extension, so it's extended to all of you. The last 2 problems on the mission, we haven't covered the thing you need to do it yet. We will shortly. So, and I do think you can finish those 2 problems in about an hour, maybe less. They're not that hard, I don't believe. Tomorrow. Yeah, because I want to keep the quiz separate. My apologies for giving false hope. But I really want to post a solution to these 2 problems also, so you have for them to study, you know. The whole mission is, you can turn it in tomorrow. Is that better? Yeah. Okay. I know, I'm giving it back to you. There you go. Mary? Yes, no, maybe so?
I guess I didn't really see
Yeah. So what this is saying is that if we add up the change in the argument of f of z, it counts the number of zeros minus the number of poles for the function within the curve, right? Like, so let me just make up an example. Oh, this probably will go badly, but let's see here. I don't know. let's make up something that we, if we did like, z over, say, z minus 1, and we'll square it. And we'll put a cube upstairs. I'll tell you, I'm going to unsquare it. Z cubed, all right? So if we look at, for example, so suppose this is 2 and this is 0, right? So we've got like modulus of z equals to 2. Then this theorem says that the integral of the differential of the argument of this function, right, is equal to 2 pi times what? What's the number of zeros?
3 minus 1. Well,
So-
3 zeros.
Yeah, so 3 zeros and, yeah, 3 minus 1, just like you said. Yeah.
How'd you get 1?
So like this has z naught equals to 0 with, a triple root, if you like, multiplicity 3, and z1 equals to 1 is a simple pole. And those are both relevant because they're inside the circle, right? But the claim is if we were, say, to do around, say, the circle of radius, 1/2, right? What am I doing? I got a double dz. That's not good. All right, let's try that again. Differential. There's no dz past the differential. Then this would be what? 2 pi what? Right, so the singularities here are at the origin. Not singularities, there's a 0 at the origin, right? And there is the singularity of 1. All right, so that's like here. So this would be what? Supposedly just 3 minus 0, right? And this is also, of course, going to be the integral of, f prime of z dz over f of z if we were to calculate it, It might be interesting, I don't know, possibly interesting to calculate that, I don't know. On the other hand, we could also just calculate the, we could try to understand the differential of the argument directly as well, right? So like, if you're on, it might be kind of tough actually to do the direct calculation here, honestly. Let me just try, and if it's too hard, we'll give up on it, okay? So if we're on the modulus of z equals to 2, we can write z is equal to 2 e to the it, right? For 0 less than or equal to t less than or equal to 2 pi. And so if we look at f of 2 e to the it, what do we get? We get 2 e to the it, right, cubed, divided by what? 2 e to the it minus 1. Oh, I don't need parentheses down here, right? I mean, I don't need these parentheses. Yeah. So, so this is what? 8 e to the 3it divided by 2 e to the it minus 1. On the other hand, this one, if I was look at the half, right, 1/2 e to the it, that would be the, you know, for the smaller circle, we would have, you know, 1/8 e to the 3it divided by what? 1/2 e to the it minus 1. Happy? Oh, man.
So is this how you're supposed to do problem 89?
Zeros of a
No. No.
No.
No.
What?
So I'm going to have to make the final no calculator. Let's see here. So think about how this works. You know, if you were to graph this, you know, if you could think about graphing this for a second. If we think about the denominator, 1/2, and I'll write it out for a second here. We got cosine of t plus I sine of t minus 1, right? Think about that. You've got cosine of t over 2. Excuse me. Oh, sorry about that. Internet. Well, I mean, it's okay for you guys, but I just sneezed into the mic. Like my mic is here, and I just did this. Like, if you're in headphones or something.
I thought you were saying that was the reason you sneezed with the internet.
Oh, the internet's making me sneeze today. That would be, I guess, I mean, if you believe in that sort of thing, I suppose. But so notice that this is definitely where this is most assuredly negative, right? You can't get a positive. Now this oscillates between plus or minus 1/2, right? So if you were to graph the denominator, basically you're, I don't know exactly. It's just over here somewhere, right? And it's stuck between, you know, minus 1/2 and 1/2. But the larger point is that the argument of the denominator, I'm going to call it Pac-Man, is essentially, you know, what, minus pi over 2, you know, to say pi over 2 to 3 pi over 2, right? Plus 2 pi z. All right, fine, there. My point is, it's over in quadrants 2 and 3, I think you. So what's the argument of a quotient? Right. So it's the argument of the numerator minus the argument of the denominator. So what ends up happening here, if you were to analyze it more carefully, is that this doesn't give you an overall change because it just stays over here like this. But on the other hand, the argument of the numerator pretty clearly cycles through 6 pi. Because it starts at angle 0 and then it goes around and around and around 3 times. It goes through 6 pi radians. But the denominator doesn't. This one up here is more complicated. The numerator still goes through 6 cycles, but the denominator, if we studied it more carefully, actually goes like one cycle the other way. So the net argument ends up being 4 pi. I know this for sure because I know the argument principle number 2, not because I've analyzed that carefully. To analyze that carefully, well, let me just show you a picture, because this is like one of those things where I use, this is one of these places where Desmos is like super helpful. So the thing is, we don't actually have to I would say, okay, it goes both ways, I suppose. On the one hand, if you know the zeros and the poles, then you can calculate the change in the argument, right? So that's nice. It goes both ways, though, right? Because this gives us a really non-trivial connection between the net change of the argument of the function, right, over the curve, and also the number of zeros and the number of poles. So I think that's a kind of surprising connection. So let's see if I can find it. All right. Come on. So here's the example I have in the notes. And since I just made up an example, I'm just going to look at this one. So here, I have z cubed plus 1, right? And I'm looking at a circle based at z naught of radius r once around, positive orientation. If I plug that in, I get f of gamma of t is, so I put z naught equal to 0 and r equal to 2, that gives me 8. It's too bright. I'm going to find like a medium green laser. All like green lasers are super bright. See how, but this one's like slightly too dim. I don't know. Whatever. So when I plug in, 2e to the it, I get this, right? Then the question is, what kind of path does that trace out? This one's a little bit easier to analyze, right, than the previous one that I have covered up on the board right now. So I say that this point covers a circle centered at 1 with radius 8 3 times. I guess that's actually fairly obvious, right? See that? Circle, the center's 1, and we're going plus 8 3 the it, so it just goes around the circle 1 2 3 times. So that means that the argument of f of z has increased 6 pi along gamma, which tells us that the number of zeros minus the number of poles is 3, and since f is clearly what? Doesn't have any poles, right? It's an entire function. That means that we have 3 zeros for z cubed plus 1 within the circle of radius 2, right? Of course, this isn't surprising because we know how to find the 3 zeros with our calculator. Because we only use our calculator, we don't try to learn any complex analysis in complex analysis, because that's just, how to be a good, it's just kind of complex, yeah. Yeah.
You could just do like a higher than 3 powers, because my calculator only goes up to cubes. Don't get my ideas, Violet.
Okay.
It's better than him taking away our calculators. No, you could just take away your No.
So, all right, so on the other hand, if we were to look at radius 1 and the center being minus 1, then gamma of t would be, minus 1 plus e to the it. And when I plug that in to this function, what do I get? I get this mess, right? And then it's like, well, what happens graphically if you have 3 e to the it, e to the 3 it minus 3 e to the 2 it plus 3 e to the it minus 1 plus 1. Well, this is easy enough, right? I could have simplified that, I guess, but I mean, this is kind of a mess. Like, what does this happen? Well, I don't know. So I used, I guess I used GeoGebra. Dr. Wang would be proud. And it ended up giving me this, whatever this thing is, a cardioid maybe? And like that. And so and that shows that it only encircles the origin just once, so the change in the argument is 2 pi. Which makes sense because this circle that has center -1 and 1 only encircles one of the zeros of this function. All right. So yeah. All right. So all I'm trying to say is that direct analysis of the change of the argument of a given function around a given circle can be challenging because you're trying to understand how the angle of the expression changes as you go over the path, you know, and I think it's a challenging question in general. So that brings us to Rouche's theorem. So Rouche's theorem is this. It says, let D be a bounded domain with a piecewise smooth boundary, boundary D, and let, oh man, this thing is, let me put this away. I started to get motion sickness, you know? Oof. So here we go. So here, let me write out Rouche's theorem for you guys. Let D be bounded domain with piecewise smooth boundary. Let F and H be analytic, or if you like, holomorphic on D union the boundary of D. All right. If the modulus of H of Z is strictly less than the modulus of F of Z for Z on the boundary, all right, then F of Z and F of Z plus H of Z have the same number of zeros in D, counting multiplicities. So the proof is going to use the argument principle, all right? So before I do that, though, let me just talk a little bit about the idea here. The idea is we have some function f, and typically our choice of the function f will be it's something relatively simple to understand. And then the h of z we think of as being a perturbation. It's a modification of the function to something uglier. Typically what we're faced with, we're going to, you're given something ugly, and you think of it as f of z plus h of z, where f of z is something pretty and h of z is the rest of it. That's our typical application of this theorem. All right, so here's the proof. So we begin with our assumption that the modulus of h of z is strictly less than the modulus of f of z, all right, for all z in the boundary of D. And I say that that implies that f of z is not equal to 0 for all z in the boundary of D. All right. Furthermore, f of z plus h of z is not equal to 0 on the boundary of D. Is that clear? There's a little contradiction proof to do here, right? So let me just show you it. Suppose there was a z where this was equal to 0. What would that mean?
Someone their moduli would be 0? Or no, the moduli themselves.
A little bit off. A little off. So this means that f of z is equal to minus h of z for that z, right? So therefore, the modulus of f of z is equal to the modulus of h of z for this z. I'll call it z1 for the sake of specificity. But that's a contradiction, because we are given this, right? Okay, so therefore, both f of z is not equal to 0 on the boundary. I mean, do you see why that is also true? If f of z was equal to 0, then you have the modulus of f of z is 0, right? What positive number is less than 0? Nothing, right? So this is impossible. Yeah, so, all right. So we have both f of z and f of z plus h of z are both non-zero. So then for z in the boundary, we can do a calculation. Let's do it. So here it goes. For z in the boundary of D, we have f of z plus h of z is equal to f of z times 1 plus h of z over f of z. Notice that since we're given, let me call this thing star. Notice star implies that the modulus of h of z over f of z is what? If I divide f of z to the other side, I have that this is less than 1, right? Which tells me that 1 plus h of z over f of z, what does it tell me about that? If this has modulus at most 1, not even that, right? Can it cancel out the 1 in terms of the real part? I mean, h of z over f of z is complex, so it could have an imaginary part, of course. But the real part of it, it can't be more than 1. Can't be less than minus 1, right? So there's no way you can cancel out the 1. This has, let me put it in here, real part of this has to be positive. Right? There's no way you can get the real part negative because this piece doesn't allow for a real part which is negative and larger than minus 1 or equal to minus 1. So let me put that into words. This tells me that all the values of 1 plus the quotient h of z over f of z fall in the what? The right half plane. Okay. What's the argument of f of z plus h of z equal to, though? See, the argument of that is equal to the argument of f of z plus the argument of the thing in the square brackets, which we just argued is relatively boring in terms of argument, right? So this is, a general identity. Well, excuse me, not a general identity. This is true for where. There's terms and conditions apply here. This is for what? This is for z on what? Well, excuse me. Fine, I guess I do need to be on the boundary of D. That's where I know I can divide by the f of z. Fine. So this is for z in the boundary of D. Yeah. Okay? So if we integrate this over the, well, let me save myself some writing, right? So what happens if we integrate both sides? What do you get? Right, take the differential. This piece integrates to 0. Why? Because the change in that argument can't ever be, it doesn't encircle. So this just integrates to 0 because it's always in the right half plane. Right, so like, this is a closed curve, right? So you're going to go back where you start, but you never encircle the origin with this piece. So that piece integrates to 0. But how about these two pieces? Well, by argument principle number 2, what do you have? This is what? 2 pi. So you got, 2 pi times the number of zeros for f plus h is equal to 2 pi times the number of zeros for f alone. And there are no poles for either one of these because we assume that they're what? They're analytic, right? So f and h, they're analytic. There's no poles here, so the argument principle number 2 just gives us the number of zeros being equal for both, and there you go. That's the proof of Rouche's theorem. All right. So let's look at an example. See, we can't be sure that an integral around a loop of an argument is necessarily 0, right? We need some kind of information like this to be sure that it's 0. That forbids us from encircling the origin and picking up a non-trivial contribution from that piece. So here we go. Example. Is this example 2? All right. So here I have p of z equal to z to the 11th plus 12 z to the 7th minus 3 z squared plus z plus 2. And we're supposed to find number of zeros within the unit circle. So what do you guys think? What should we do here? So like you think of the idea, all right, is that p of z is going to be our f of z plus h of z. And we're going to use Rouche's theorem, right? And we need what? We need that what's the condition? We need that the perturbation, the extra piece, the h of z, has to be strictly less than the f of z, whatever that is. Right? So if you look at this, and also for this to be a good argument, we need to know a simple way to calculate the number of zeros for whatever our choice is of f. Right? We need this kind of bound, and we also need a simple method, you know, to see what the number of zeros is. So I think it kind of just yells at you, like this piece right here is bigger than the rest of them, right? Like 12 is certainly bigger than 1 plus 3 plus 1 plus 2. So we should be able to use that piece. And also, what's the number of zeros for that? If I say f of z, so I'm going to choose f of z is equal to 12 z to the 7th, right? And then the number of zeros is what? 7, right? Because 12 z to the 7th has the origin as its 0 with order 7. So if I do that, my h of z is what? Yeah, everything else. So I got z to the 11th minus 3z squared plus z plus 2, right? So suppose modulus of z is equal to 1. So the modulus of h of z is equal to the modulus of z to the 11th minus 3z squared plus z plus 2, right? That's less than or equal to what? Modulus of z to the 11th. I'll put it in a step here. Z to the 11th plus the modulus of minus 3z squared plus the modulus of z plus 2, right? By the triangle inequality. But by further properties, wait a minute. No. You're the yawner.
What?
You were the one who yawns.
No.
Someone was yawning the other day.
I did yesterday in DPQ a lot.
That was where it happened. No, wait a minute. No.
No, it was complex.
It was complex.
Oh no, it was me last time, I think.
Yes. Or was it? As I just observed this one.
She's not taking notes, that's why she's tired.
I need to start assigning points for notes.
Yay! Yeah, let's do that. I always take notes.
Just messing with you guys. So this is equal. Well, I mean this is straight up equal to 1 plus 3 plus 1 plus 2, right? Because if we have the modulus of z equals to 1, then these literally simplify to that, yeah? So 4, 5, 7, right? But the modulus of f of z, which is equal to the modulus of 12z to the 7th, is equal to 12 for modulus of z equals to 1. So therefore, the modulus of h of z is less than 7, which is clearly less than 12, which is equal to the modulus of f of z. Hence, p of z has 7 zeros within the unit circle, counting multiplicity by Rouche's theorem. See what I did right there? That's called writing a conclusion. Something you guys should think about doing.
What did you say that the modulus of h of z is equal to 7? Or is it still going to say
Less than or equal to? I don't know. Oh, yeah, fair enough. true. But that matters not because this is, I'm pretty sure, a strict inequality, right?
Okay.
Unless you're going to think of 7 as a variable, but that student is long gone, so we're safe. I used to have a student, anytime I asked for the name for a new variable, he would suggest 7.
Really?
And I said, Joe. No Joe. But Joe went to Australia.
Protected about my.
Joe went to Australia before COVID, so the joke's on him. But anyway. It seemed like such a free place before the COVID insanity. I saw them chasing people down in parks and stuff, and like the monitoring of COVID people in Australia was like next level.
Really?
Yeah.
Yeah, they have robots.
How many times do I have to say COVID before I get a warning label on this video? COVID, 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 jab, jab, vaccine denial, jab, jab, COVID, COVID. Would that be enough? Would that do it? It would be awesome if that's enough to get like a disclaimer, like get the bar, you know?
Not factual.
That was just some popularity.
I should get some like goofy emoji of like a syringe and put it in the thumbnail, you know? Sorry, I'll stop. All right, let's do another example. Can I erase this one?
No.
Oh, okay. Oh.
Well, my phone's doing that and difficult.
Rouche's theorem can be used on non-polynomial examples. You just, have to, and it doesn't have to be used just on circles either. Like there are other regions. It can be used in a limiting sense, much like we've been doing integration, Most of our integrals that are interesting lately, we set up some kind of finite integral and then take the limit as the thing gets huge and discover something interesting. So here's another example. Example 3. So here we're supposed to prove z plus 3 plus 2e to the z equals to 0 has precisely one solution in the left half plane. All right, so the idea here is going to be to look at, so first of all, how do we get the whole right half plane? Like what we're going to do is we're going to think about going from, say, IR down here to like minus IR. Take a semicircle like so. That was supposed to be a circle. Oh well, I tried. So we're gonna look at let's see here, like this. So we've got this is the inside of the region, right? So let's see here. If we let R go to infinity, right? So here's like the origins in the middle here, right? If we let R go to infinity, what happens? We'll get the whole left half plane, right? So as you look at the given expression, you want to think of, for Rouche's theorem, what we're going to do is we're going to think of this piece right here, right, as the f of z, and we're going to think of this piece over here as the h of z. Okay? And so good news, h of z is definitely not equal to 0, right? Because the exponential is never 0. F of z, on the other hand, is 0 where? Minus 3, right? So if this is minus 3, we have f of minus 3 equals to 0. Great. So maybe this will work. But what do we need to come up with, though? What's the tough part? We need to show that, you know, so if I call this D, all right, maybe D sub r would be more honest, then the boundary of dr is what? We have this, like, let's call it CR for the circle, and also the minus IR to IR for the line segment. And so that's the boundary. We've got the circular part, and we've got this part, right? So this part, we have typical point, what, Z is equal to, how's it go? IY, right? Minus R less than or equal to Y less than or equal to R. That describes these points, right? Over here, typical point is what? Z, how's it go? R e to the IT for what? Maybe pi over 2 less than or equal to t less than or equal to 3 pi over 2, right? We could do that. So I think probably we want to, like, divide and conquer in terms of the verifying. We need what? We need to show that the modulus of h of z is less than the modulus of f of z for all z in the boundary. Right? That's what we're trying to show. Once we've shown that, then we can apply Rouche's theorem, right? Because both f of z and h of z are entire functions, which means they're analytic everywhere. So once we verify the condition of Rouche's theorem, we can put it, we can use it, and we'll have proved what we want to prove. Agree? Disagree? All right, so let's look at minus IR to IR. There we have f of z, well, f of iy equals to what? Iy plus 3, right? So if I look at the modulus of that, what do I got? I mean, it's the square root of 9 plus y squared, right? And if I'm right. On the other hand, 2 e to the iz, well, e to the iy, right, is equal to what? Let me rewrite that. The modulus of h of iy is what? It's equal to modulus of 2 e to the iy, right? But that's just strictly equal to 2, right? Notice that the square root of 9 plus y squared is just by calculus 1, whatever you want, common sense, greater than or equal to 3, right? So 2 is definitely less than 3, which is less than or equal to modulus of f of iy, right? So that checks for the vertical part, right? So case 1. Case 2.